Okay, thank you, sir. So let me start, sir. I have presented the screen so that you don't see my face because that would be more charming than my face. Now, uh, respected speaker, other dignitaries, friends, ladies and gentlemen. Good afternoon, everybody. On the 24th of March 2020, the Prime Minister of India announced 21 days of lockdown all over the country. Today, 5 months and 5 days later, well, the 24th of March 2020, still we are undergoing Prime Minister of India unlock number 3. No schools, no classes, no trips, announced no functions, nothing. In fact, UL Space today conducts around months and 3 days space camps every year, most of which are residential in nature. And now, well, why speak of camps when you can't even go out? But as they say, when the going gets tough, the tough gets going. And it has been 14 weeks since we, UL Space Club, got going with our exclusive webinars every Saturday, exploiting the opportunities that the lockdown provided despite the many hardships. Trying to rejuvenate the system to what we see today. The past 14 weeks has witnessed 11 beautiful sessions from top professionals, and now, well, who are the best in what they do. And we've even seen of camps when you some sessions from students of UL Space Class they say in, one of which happens to be myself. We underwent multiple phases of transformation after redefining this as a national webinar in English language. We felt the necessity of an exclusive Malayalam webinar, which was beautifully executed the previous Saturday with Sri Radhakrishnan sir, giving us one of the best sessions so far. Over the past couple of months, we've had the opportunity to get in touch with a handful of smart kids who joined our subwing named Cosmos, and the curiosity, talent, and developments are evident from our Q&A sessions, which you will see later on today, as well as their performance in the UL Space Quiz that follows this national webinar in English language. Today, we're extremely happy and proud to present our speaker for the day, Dr. Anand Narayan, Associate Professor, IIT. It's my honor to welcome you. Best sessions. We also have an experienced panel of veterans from ISRO and scientists from top universities inside and outside the country. We welcome all of you to today's session. Our participants can also talk to our chief patron and mentor, Shri E.K. Kutty sir, former director ISRO. This session is moderated by Shri Yukesh Chadil sir, and later on, the question and answer session will be moderated by Master Sriram D. We also have Shri T. Damodaran sir, who is representing UL Education. We expect a cracker of a session today, and I happily welcome all our participants to UL Space Club Webinar 15, Exoplanets and the Search for Habitable Worlds. Before moving into further proceedings, let me take a few moments to announce the results of UL Space Quiz 14, Science Tomorrow. As you may know, after every webinar session, we have a quiz competition over Google Forms. The participants may attend the questions based on what you've learned today and some other general knowledge based on the topic of discussion. The top 3 will be selected based on their accuracy and time of submission. The first prize winner will also receive a cash prize, which is sponsored by Cinderway Nurture. You will receive the link to the quiz in the chat box towards the end of the session today. And most importantly, the link will only be activated once the session is concluded today. Now, here are the winners of UL Space Quiz 14. Now, let's go the conventional way. Let's start from number 3. The third prize is for a student who has been very active in all our activities in the near past, and he is Hardik S. Nair, and he's a 10th standard student at GHSS Kokalu. The second prize has been bagged by a very close friend of mine, and he is Anand Krishna, and he's a 12th standard student at Perambra HSS. The first prize, you might have just seen a peep, but that person has been getting the first prize multiple times. So there is no need to introduce him again and again. And the first prize for formality is for Febin Firshad, and he's a 10th standard student at Memunda HSS. Now, congratulations to all winners and all participants, and best of luck to all of you for today's quiz as well. Now, today, After Dr. Anand Narayan's talk, we'll have a Q&A session, which is otherwise known as the question and answer session, which will be moderated by Master Sriram D. The participants are requested to post your questions in the chat box first. Now, you can post your questions anytime, and it can be in English or Malayalam, but take care to type the questions in their respective alphabets. Like, avoid typing Malayalam questions using English alphabets like the way we are used to in chatting. That is because it is better for translation and purposes. The best questions will be articulated and will be asked to the speaker and our panel of experts that we have today. Now, today's session will be followed by the 15th edition of UL Space Quiz, as I mentioned earlier, and the announcements of UL Space Club Webinar 16, which is going to be conducted the next Saturday, will also be given. Now, we request all participants to make sure that your mics are muted and your cameras are off during the talk, and also take care not to present your screens. If you have to rejoin anytime during the meet, take care to click only on join and never ever click present. Now, requesting all of your cooperation. Without further ado, let me invite Shri UK Shajit sir to introduce our speaker and to illustrate the redefined system of our webinar series. Over to you, sir.
Thank you, our dear Bharat. And today, the 15th day of our webinar, we started in the COVID period. And the topic is exoplanets and the search for habitable world. And man is so curious to know about what's around him, and he explored the land and water and now space also. And he is searching for new space and little bit anxious about life in other planets. Today we have Dr. Anand Narayan, Associate Professor in Astrophysics, Indian Institute of Space Science and Technology, and to speak about these curious substances. And before that, let me say something, few words on Indian Institute of Space Technology. That's at Trivandrum in Kerala also. And most of our students are space aspirants and they want to get a chance in the ISRO. So IIST functions as an autonomous body under Department of Space, Government of India, and it's nurturing the high quality manpower for Indian Space Research Organization. And that's why we selected this eminent person from the ISSQ also. He's a working person, still conducts his search and about the exoplanets. And when we take his academic track, that's a good exemplary track he is having. And he started his journey in technical education from CET Trivandrum in BTech Electrical and Electronics. And wonderfully, he switched over to the world of astronomy and astrophysics. That subject was so curious in him, and he nurtured that thing. And before, rather than turning into a techie, he turned to become a scholar and a master in astronomy and astrophysics. He was selected to Pennsylvania State University, USA, and he worked there a lot. And he has experience as assistant professor, Department of Earth Science and Space Science, IIST. And before that, he was assistant scientist in Department of Astronomy, University of Wisconsin, Madison, from 2008 to 2010, and is a graduate researcher, Department of Astronomy and Astrophysics, Pennsylvania State University. So he is having national and international exposure in this regard. And let me mention something about his research also. His research is in studying the properties of diffuse gas in intra-galactic medium and regions surrounding galaxies. And for this, he relies on spectroscopic observations. He has made use of optical and ultraviolet spectra of coils obtained from ground-based facilities like VLT and Keck telescope and space-based observation like Hubble telescope and fused satellites. And still, he is searching for the news for new planets and even from the light from the signals and the lights analyzed by his team. And he is interested in outreach activities. That is evident from his acceptance of our invitation to this webinar. That's why he wanted to nurture the students, and he continues his journey, and he has done a wonderful thing in Malayalam documentary for television named Agalangalile Prapancham. That shows his this interest in nurturing our students, and he has made a documentary film on history of Travancore Observatory. And that is the history, and we proudly welcome Dr. Anand Narayanan to our UL Space Club and to this webinar also. A warm welcome, sir. And we had panelists in our webinar. From this webinar, we excluded the panelist as a practice, and because our participants are so enthusiastic to ask questions, and from day onwards, we have one reporter to dilute the technical complexities in terms of topic. And he would assist the students and participants in understanding and asking questions. Today we have Sri K. Jairam, former Deputy Director of ISRO, and is part of our UL Space Club as rapporteur. And he will assist us after our chief guest talks. Then we have our Kuti sir, the chief mentor of always with us, and we'll continue this journey of search for exoplanetary search, guided by our chief guest. And after that, we'll have a quiz, as already mentioned. In that quiz, the winners will be declared in the next coming webinar. And I invite all the dignitaries who are participants in this webinar, and they are continuously supporting us for the past 15 weeks. And we welcome all of you. Some of them are great veterans of INSRO and some other science institutions. And we are happily welcome you all to this webinar. And I invite all, for all of you, our chief guest, Dr. Anand Narayan, to deliver his wonderful speak to our participants. Welcome, sir.
Thank you, sir. Thank you for that generous introduction. Good afternoon, everyone. It is a great pleasure and an honor for me to be part of this webinar series that UL Space Club has been conducting for the last several weekends. A special thanks to all the students who have worked behind the scenes, Bharat and Varun and many others, to make this happen. I think it's a really commendable effort from all of them. And a special round of applause for all the students who have tuned in from within Kerala and from other states of Kerala. This lockdown has been very difficult, especially for the students, because all their classes are online and they are stuck to computers from morning till evening, attending their regular classes on weekdays. And now they have come for this webinar for a weekend also. So that shows the amount of commitment and interest that you have towards science and astrophysics. So thank you for that. And before I forget, happy Onam to all of you, those of you who are in Kerala and rest of India. Okay. Have a wonderful Onam holidays in the days ahead. What I'm going to talk about, as it was mentioned in the introduction, I'm an astrophysicist. I teach and I do research in astrophysics at the Indian Institute of Space Science and Technology here in Trivandrum. And astrophysics, for those who are familiar with that term, astrophysics is a way of the laws of physics. So in astrophysics, we try to find answers to questions about the universe. For example, has evolved over time, how old is the universe, how matter was created, how galaxies and planets formed in the universe, what will be the fate of the universe, will the universe continue to exist like this forever or will it ever end? And above all, are we the only sentient beings in this entire universe who are asking these kind of questions? In other words, could life be present anywhere else in the universe? So through astrophysics, we are trying to find scientific answers to these kind of really profound questions that the human mind has ever asked. And what I'm here to talk about this afternoon is an area of research and discovery in astrophysics that has been gaining of late, very recently, a lot of public attention. This is a really fascinating development that has been unfolding in the field of astrophysics for the last 25 years, and that is the discovery of extrasolar planets. Sometimes they are also referred to as exoplanets. Extrasolar planets is the collective name, is the umbrella term for planets that are orbiting other stars. Beyond the PowerPoint. Question for a very long time as to whether any of these stars that we see in the night sky, they have planets or not. But it is only in the last 25 years or so that cutting edge technology in optics and telescopes has enabled astronomers to discover extrasolar planets. Now, what I'm going to present today is an overview of that story of how astronomers made those discoveries. Now, as it turns out, finding extrasolar planets, that is planets orbiting other stars, it's not an easy task. One cannot see planets around other stars just by pointing a telescope at the star. There are some difficulties, there are some great barriers in finding planets around other stars. So I will go over some of the difficulties in directly taking pictures of extrasolar planets. I'm sure most of you would have seen one version or the other of this kind of an image. Okay, so the purpose of this is an image to scale.
Excuse me, sir. Sir, can I please intervene for a moment?
Sure.
Sir, your presentation has just been lost. Can you please present once more, or the participants can please spin the presentation? Because somebody tried to present their screens right now and the presentation has been lost.
Okay, I'll do that again, no problem.
So it's a request to the participants, please don't click on the present option, because if you present the screen of Anand Narayan sir's screen will be lost. So please don't click on present. Excuse me, sir. Gayatri Tiruvallur. That account has been trying to present twice. Please don't do that. Shajil sir, can you please take care of it?
I'll remove it.
Yeah. Now can you see?
Yes, sir.
Yeah. So I'll continue.
It's okay.
Yeah. So the purpose of showing this figure, all of you must have seen this picture before. This is a picture of the planets of the solar system at the bottom here and the sun. And this picture is to scale. Okay, it is drawn to scale. The relative sizes are exactly correct. And so the purpose of showing this particular picture is to remind ourselves that planets are incredibly small when compared to stars. Okay, if you take the sun and the planets of the solar system, Jupiter, which is one of the largest planets in the solar system, is still 100 times smaller in size compared to the sun. And Earth is 100 times smaller than Jupiter. Okay? So there's a huge difference in size between stars and planets. Okay, so that makes detecting planets around other stars an observational challenge. So that is one of the challenges. The second challenge is that the stars we see in the night sky, they are at enormous distances from us. Now, all of you may know this distance in astronomy is usually measured in light years. And 1 light year is the distance that light travels in 1 year. So light has a speed of 300,000 kilometers in 1 second. So that's the distance that light covers in 1 second, which means that light can go around the Earth 7 times in 1 second. That's what 300,000 kilometers in 1 second means. So light is really fast, and a light year is the distance that light would travel in 1 year. And most of the stars that we see in the night sky, they are at distances of hundreds to thousands of light years from us, which means that light itself would take 100 years or much more time to reach us from those distant stars. So now what that means is that even a very big star, if it is such a large distance from us, it will look like a tiny dot in the sky, even through a telescope. Even if you use a telescope, it's still going to look like a point. Now the planet, which is already much smaller than the star, is going to look even smaller than a point. So therefore, if you just point your telescope at a star, we will see the star, but it will be extremely difficult to see the planets around it. And the third and the last difficulty is that stars are very bright compared to planets. A star is usually 1 billion times more brighter than a planet. Now, 1 billion is 1 followed by 9 zeros. So if you have a planet and a star sitting right next to each other, the star will be so bright that we will be able to see only the light from the star. We will not be able to see the light from the planet. So being very small and very dim, planets are easily lost in the glare of the giant stars that they orbit. The common analogy that astronomers give is, it is like trying to photograph a firefly that is sitting next to a floodlight. In stadium, you have these huge floodlights. Imagine a small firefly, Minna Mininga, sitting next to that floodlight. If you take a picture of it, the glare from the light will be so large that you will not see the firefly. So that is the observational challenge in directly seeing extrasolar planet.
Sir, I'm extremely sorry. Can I please interview for a moment?
Sure.
Sir, somebody tried to present again and the presentation has been lost. So there is a suggestion to the participants, go to the participant details kind of window and select Anand Narayan presentation. You can pin the presentation on the screen so that it won't be lost. Sir, I think your presentation is gone.
Yeah, so I closed it. I will start it again. Don't worry.
Sir. So next time when he presents it, the participants, please take care to pin the presentation.
Okay.
There has been a query in the chat box, like from someone who said we can't see your presentation. So the problem is that someone tried to present. So next time, okay. Now the presentation is switching on. So all participants, please try to pin it. You can see the pin kind of option when you try to move your mouse pointer across that. So pin it. Over to you, sir.
Yeah. So now my slide can be seen, right? I hope everyone is seeing the slide.
Yes, sir.
Yeah. Thanks, Bharat. So to sum it up, as I was saying, it's very difficult to directly see extrasolar planets around stars. And this video, what I'm going to show next is a video. Depending on your bandwidth, you may be able to see it nicely, or sometimes there may be a jerk. But this video is essentially to sum up the difficulty in finding planets around other stars. So imagine that this is a star and that is a planet orbiting around that star. This star-planet system is going to be at a large distance from us, okay, hundreds to thousands to even tens of thousands of light year distance from us. So for an astronomer who is sitting here on Earth and looking at stars with the help of a telescope, the star itself will look like a point source, like a dot in the sky, and it will be very bright. Okay, and so a planet that's sitting right next to it will be extremely difficult to see. So when we take deep photographs of the night sky, we will see the stars easily, but not the planets around them. So what that means is that direct detection of extrasolar planets by taking photographs is extremely difficult. That doesn't mean that we cannot discover extrasolar planets. As it turns out, there are some very interesting indirect methods for finding exoplanets or extrasolar planets. Okay. There are about half a dozen techniques, but what I'm going to go over are 2 techniques that have been most successful in finding planets orbiting other stars, in finding extrasolar planets. Okay. And these techniques are called indirect techniques or indirect methods because using telescopes, we will be observing stars and not the planets around them. Based on our observation of the star, based on monitoring the behavior of the star, we will make the inference, or we will arrive at the conclusion that there is a planet orbiting that star. So it's an indirect way of confirming the existence of a planet around a star by observing the star. Okay. Since we do not directly see the extrasolar planet, it's called an indirect method. Both these radial velocity method and transit method, these are called indirect methods of finding extrasolar planets. Now, first we will look at radial velocity method, then we will talk about transit method. I'll only give a very brief overview of them. Okay, so each one is a very involved technique. So to understand radial velocity method, for those of you who are school students in this audience, to understand this method, you need to know the concept of center of mass. What center of mass means. So here is a picture of two people sitting on a wooden plank, okay, or a wooden board like this. And if these two people are of equal weight, then the point of balance will be at the center of this wooden plank, center of this seesaw. Okay, so that will be the point of balance. Now, instead, if you have two people of different weight sitting on this wooden plank, so unequal weight, okay, the point of balance will be closer to the person who is heavier. So the point where the force due to the weight of these people would balance out, okay, that point is called the center of mass of this system. I'm sure most of you know this, so this is just a refresher. Now consider a star-planet system. The stars are obviously much more massive than the planets, so the center of mass of the star-planet system will be very close to the star, and often the center of mass will be inside the star itself. Okay. So that's what the scenario is for a star-planet system. The center of mass of it will be very close to the star. Now, in the case of our solar system, the center of mass is often called barycenter. And we can use the term for extrasolar planetary systems also, where you have a star and an extrasolar planet orbiting around it. The center of mass of it will be very close to the star. Now, the other thing that we need to remember is what keeps planets in orbit around stars. The force that is responsible for keeping the planets in their orbit around stars is the force of gravity. So the star exerts a gravitational pull on the planet, but we know that gravity is a mutual force. The planet will also exert the same amount of force on the star, with the result that as the planet orbits around the star, okay, the star will also keep orbiting. And the reason for that is that because the planet is not actually orbiting the star, the planet is orbiting the center of mass of this star-planet system, which will be somewhere here, center of mass, outside the star. So the planet is orbiting the center of mass, and the star also will be orbiting the center of mass. Only then they will form a dynamically stable system. Okay, so held by gravitational force. And so when we are observing a star, if there is a planet going around that star, as seen in this animation, okay, forget what is happening here, okay, just focus on the upper part of the animation. If you have a planet going around that center of mass of the system, the star will also be going around, pulled by the force of gravity from the planet, and we will see the star exhibiting this kind of a wobbling motion. Okay, where sometimes the star will be going away from us, sometimes the star will be coming towards us, at other times the star will be once again coming towards us and then going away from us like this. So this is called wobble motion, back and forth motion with respect to the center of mass. By observing this wobble motion, one can infer the presence of a planet around the star, even if we do not directly see the planet. Now, the way this wobble is measured is using telescopes. Okay, if you just look with your naked eye, you will not see stars wobbling because they are at enormously large distance from us. You need telescopes and instruments connected to that telescopes. So the wobble is measured by collecting light from the using telescopes and recording the spectrum of stars. So let me just quickly explain what I mean by spectrum. So by the way, this wobbling motion, it's called different names. Sometimes you call it wobbling, sometimes you call it wobble motion, sometimes it's also called reflex motion, which is the star going back and forth with respect to the center of mass. So what is a spectrum? Okay. I'm sure all of you have done this experiment where you use prism to split light, sunlight or any white light into its component colors. This is an experiment that we all do in school. So splitting of light into different colors is called dispersion of light. Okay. And the colored light that we see after the light passes through a prism or some kind of a dispersing element, that light, the colored light, is what is called the spectrum of this white light. And spectrographs are instruments that are capable of splitting light into different colors as shown in this picture. Okay. So what astronomers do is they use telescopes to look at stars, and the telescope collects the light, and the light is sent to a spectrograph. The spectrograph produces or renders a spectrum of that star, and it is based on that spectrum that astronomers figure out whether the star is exhibiting this wobble motion or not. So I don't know how many of you have, whether you have seen any astronomical telescopes. So I'll just show you some pictures of how telescopes that astronomers use look like and how spectrographs look like. Okay. So this is a photograph of a telescope that is owned and operated by the Indian Institute of Astrophysics in Bangalore. It's called the Himalayan Chandra Telescope. It is situated in Ladakh, which is in the northernmost part of India on the Himalayan mountain ranges. So the telescope is housed inside this dome structure. If you look inside, okay, you will see a complicated optical arrangement, which is what the telescope really is. So it's quite different from the telescopes that we use for stargazing in our schools and astronomy clubs. These telescopes are heavy, big, bulky instruments with a lot of plumbing and other electronics going into it. And the purpose of the telescope is to collect the light. The light that is collected is sent to a spectrograph, and spectrographs look like this. They are usually kept in a vacuum chamber to minimize external factors affecting the measurement. So here is an example of a spectrograph. It's called HARPS, High Accuracy Radial Velocity Planet Searcher, which is used for detecting extrasolar planets. So if you split open this cylinder, you will find that it has lots of optical elements, lenses, mirrors, focusing elements, etc. Optical fibers, many things are there. So this is what a spectrograph looks like. So it's not as simple as just a prism, but its functioning is very similar. The light that comes into the spectrograph, it is split into component wavelengths. Okay. So let's come back to this radial velocity method. So I'm going to play an animation here to explain how radial velocity method is used to infer the presence of planets around stars. So here is a star, and here is a planet that's going around that star. In reality, the star is going around the center of mass of this system. The planet is also going around the center of mass of this system. So our telescope will be looking only at the star. Okay, we don't know whether there is a planet around it or not. So our observation is confined to the star. The telescope collects the light, it sends it to a spectrograph, and the spectrograph produces colored pattern like this. Now, if there is a planet that is orbiting the star, then the star will not be stationary. It will be moving back and forth. It will be doing this wobbling motion as shown here. And when the star is doing this wobble motion, notice what is happening to the spectrum. I'll just play this video once again. When the star is swinging towards us, we see that the light from the star is getting shifted towards blue. And when the star is moving away from us, we see that the light is getting shifted towards the red part of the spectrum. So this is called blue shift and red shift. It's a property that sources exhibit when they emit light and when they are moving towards us or away from us. Now, by measuring this shift, this shift in light, in the light pattern in the spectrum of the star, astronomers can infer that there is a planet orbiting it. The bigger the shift in light pattern, the more massive this planet is. The smaller the shift in the light pattern, the smaller the planet that is orbiting it is. And also, the longer it takes the longer it takes for the light to go through these shifts, the farther away the planet is from the star, the shorter the time scale for the light to shift from blue to red and back to blue and again to red, the shorter that time scale, the closer is the planet from the star. So by observing the shift in the spectrum of the star, astronomers will be able to infer the presence of planet, how big, how massive it is, and also how far away it is from the star. Now, I have to emphasize here that I have only given a quick overview of the radial velocity technique. The actual measurement is very, very rigorous. The shift in a star spectrum is a very delicate effect that astronomers measure, and so there's a lot more to this story, but since we don't have time, I'm just giving you an overview. So this radial velocity method has been hugely successful in finding planets around other stars. In fact, the first extrasolar planet around a sun-like star was discovered using this radial velocity method. The discovery was made in the year 1995 by two Swiss astronomers. The star around which the planet was discovered, the star is called 51 Pegasi. That star is about 50 light years from us. So these two Swedish astronomers, they were recording the spectrum of the star for several consecutive nights, and they found that the light pattern, the spectrum from that star exhibits this blue shift, red shift, periodic blue shift, red shift. So they found that the star is wobbling and it's showing this reflex motion, which led to the discovery of this first extrasolar planet back in the year 1995. So this video shows where in the sky 51 Pegasi and that extrasolar planet is. Pegasus is a huge constellation. If you look in the direction of Pegasus, you'll find that there is a star that looks more or less similar to our sun in terms of its surface temperature and size, etc. That is 51 Pegasi. And the first extrasolar planet was discovered around that star. This is just a computer visualization. So this bright star over here is 51 Pegasi. In 1995 itself, soon after the discovery, the astronomers who discovered the first extrasolar planet, they wrote a scientific article in the journal Nature announcing to the world this discovery. So this is a screenshot of that publication. The title says a Jupiter-Mars companion to a solar type star. These are the two astronomers, Mayer and Kulos. Last year, 2019, they were awarded the Nobel Prize in Physics for this discovery that happened in 1995. So they had to wait for 25 years for the Nobel Prize to come to them. And you can see a lot of details are written here. The presence of a Jupiter-Mars companion is to the star 51 Pegasi is inferred from observations of periodic variations in the star's radial velocity. The interesting thing is the next sentence. The companion lies only 8 million kilometers from the star, which would be well inside the orbit of Mercury in our solar system. So what they were trying to say is that if you look at our solar system, let's say this is the sun, this is where Mercury is. Okay. Mercury is much closer to the sun than Earth is. In the case of 51 Pegasi, the planet was roughly half the mass of Jupiter, or it is probably even more massive. So it is definitely not a small planet like Mercury, but a large planet like our Jupiter. But it was extremely close to the star. So the first discovery itself was quite surprising because till that time, the only planetary system that astronomers knew was our own solar system. And in our solar system, we don't have anything like this, where you have a huge planet very close to the star. Now, in the years that followed, 1995, many more planets were discovered by radial velocity method. But as it turned out, almost all those extrasolar planets were similar to this. Big planets orbiting very close to their star. And the reason for that is that there is an observational bias. in the method for finding extrasolar planets, this radial velocity method. As it turns out, this radial velocity method is biased towards finding big, massive planets orbiting close to their star. If the planet is big and if it is close by, the gravitational pull on the star will be larger and the wobbling motion, this back and forth reflex motion, will be larger. So if the wobble motion is large, it will be very easy to detect it. If you have a small planet orbiting a star, the gravitational force of that planet on the star will be small, and therefore the wobbling motion will be very, very small, and it may escape our detection. Okay, we may not be able to detect such tiny wobble motion. So for that reason, this radial velocity method, even though it discovered many extrasolar planets, almost all of them were big, massive planets orbiting very close to their star. So that's an observational bias. Okay. And just to explain that point, whatever I just mentioned, I'll play a video where they show a small planet and a large planet orbiting around the star, and you can see how the wobble motion is larger when you have a bigger planet. So if the planet is bigger, then the center of mass will be outside the star, okay, far away, and the wobbling motion, the reflex motion, will also be larger. I'll play this video once again. So if you have a massive planet that is sitting very close to the star, planets of the size of Jupiter, so sitting very close to the star, then obviously the temperature is going to be extremely high because of the energy output from the star. So these kind of planets are therefore collectively called hot Jupiters. Okay, they are commonly called as hot Jupiters, and we don't have any hot Jupiters in our solar system. In our solar system, the bigger planets are all very far away from the sun. So this in a nutshell is the radial velocity method. Now I'll move on to the next technique, which is the transit method. The transit method is very simple to understand. Okay, imagine that we are looking at a star, and instead of recording its spectrum, let's say that we are monitoring its brightness, the amount of light that we are getting from the star. Let's say that we are monitoring, and as we are monitoring the brightness, suppose a planet happens to pass in front of that star, then for the duration of passing, which is called transit, for the duration of transit, a small amount of light from the star will be blocked by the planet, and we will see the light from the star decreasing for a short duration. And again, when the planet goes one full orbit around the star, and when it comes back, we will see that the light again dips. So every transit of a planet in front of a star will result in a dip in its brightness. And by monitoring constantly the brightnesses of stars and by picking out these dips in brightness, astronomers can infer the presence of planets around them. So I'll show you an animation where this transit method, whatever I just said, is shown in the form of an animation. This is just an animation, not real data. Okay? So when a planet moves in front, the brightness of the star dips. And when the planet moves out of its way, the brightness again comes back. The brightness will again dip when the planet completes one orbit and comes back in front of the star. So these are called transit events. It's not a full eclipse, but the planet being so small, it will only block a small amount of light from that star. Now the amount of light that the planet blocks is going to be determined by how big the planet is compared to the star. The dip in brightness is going to be determined by how big the planet is compared to the star. Okay. For example, if you have a small planet moving in front of a star, the dip in brightness will be small. If you have a large planet that is moving in front of that same star, the dip in brightness will be more. So the amount of brightness dip will give us an estimate of how big the planet is compared to the size of the star. So radial velocity method, the earlier method which I spoke about, that will give us the mass of planet and how far away the planet is orbiting from its host star. Transit method will tell us how big the planet is. Okay, it's very useful information. So here is how the light from a star, if you keep on monitoring it, here is how the light will dip. Okay, so along the horizontal axis, x-axis is time, along the vertical axis is brightness. So when no planet is transiting, the brightness will be constant, but when the planet transits, the brightness will dip. After the planet transit is over, the brightness again becomes normal. Again, when the planet comes, the brightness will dip. After the transit is over, it again comes back. So this repetitive dip in brightness is an indication that there is an object that is going around it, which is causing the starlight to dim. And the duration between two of these dips will tell us what is the orbital time period of the planet that is orbiting that star. Sometimes this can be few days, sometimes this can be few years. The problem with years is that you have to keep on observing that star for years. Okay. Just to give you an example, let's say that we are an alien astronomer, okay, sitting in some far corner of our own galaxy, and let's say that we are doing this brightness measurement of the sun, trying to see if there is any planet going around it. Then when Earth moves in front of the sun, when we are observing from far away, it will produce a small dip. The next time that dip will occur will be 1 year later, 365 days later. Okay. Nobody really has that kind of a time. Okay. Now, if you think about Jupiter, when it moves in front of the sun, if you are an alien astronomer looking at the sun from a distance, you will see that the sun's brightness dips. The next time that dip will happen because of Jupiter will be 12 years later. So that's a lot of time, more than 3,000 days later. So because of that, since this work has not been going on for such a long time, most of the planets that have been discovered using transit method, they are planets which are going in short duration orbits around stars. So there also a selection effect is there. Now, this transit method has also been extremely successful in discovering extrasolar planets orbiting other stars. And a particular example is this TRAPPIST-1 system. Those of you who have been following astronomy news in popular media, you must have heard of it. This discovery happened a few years ago in 2017 when the Spitzer Space Telescope, it was looking at a faint star called TRAPPIST-1, trying to see whether there are any planets going around it, trying to detect it using this transit method. And instead of finding one planet, the Spitzer Space Telescope found 7 planets orbiting around this TRAPPIST-1 star. The star itself is roughly 40 light years away. 7 planets orbiting around this one star, and all these planets were discovered by monitoring the brightness of the central star and seeing the dip in brightness. So this animation shows that all the 7 planets are orbiting, and every time a planet crosses the path of the star along our line of sight, there is a dip in brightness, which is what is shown in the bottom. Okay, so this is brightness. Whenever you see a planet transiting, the brightness dips down. So this requires a lot of patient monitoring of star brightnesses. And the other interesting aspect is that all these 7 planets of the TRAPPIST-1 system, they were all planets with sizes comparable to that of the Earth and masses also comparable to that of the Earth. So probably these are rocky planets similar to Earth, Venus, etc. Now both this radial velocity method and transit method, as I mentioned, they have been very, very successful in finding extrasolar planets, but they are still indirect methods. We do not see the planet. we infer the presence of the planet based on observations on the star. So that is what we do. What would be really spectacular or what would be really exciting is if we can actually see the planet in photographs or in images taken with telescopes. Now, as I mentioned in the beginning, there are some difficulties in doing that. Okay, planets are very small, they are very close to the star, and also they are very dim compared to the star. So it's not very easy, but in the last 10 years or so, with great advancements in optics and in the design of telescopes, astronomers have been able to take pictures of stars and planets going around them. In November 2008, a group of astronomers using the famous Keck and Gemini telescopes, they announced that they have actually seen planets orbiting a star. The star is called HR 8799, and that star in this is the picture. Okay, so here is the star. The light from the star has been removed, subtracted out, so that we can see what is around it. And when you subtract the light out from the star, when you block the light out from the star, we see 4 bright objects in that same field, and these are 4 planets that are orbiting the star. Now, how do we know that they are planets that are orbiting the star and not some background star or some foreground star? So to confirm that these are planets, one photograph is not enough. You need to keep on taking photographs and see whether you can track the motion of these planets. And from that, you can infer whether these are actually planets or we are seeing some background object, against this foreground star. So these team of astronomers, they continuously monitored this HR 8799 star for a period of 7 years. And they found that these planets, these are indeed planets and they are orbiting this star. Okay, so 7-year-long observations. Okay, so what I'm going to show next is an animation, and this is not an artificial animation. This is whatever you're going to see is real, of photographs taken over those 7 years, stitched together, so that you can actually see the planets moving. So here is HR 8799, the star. The light from the star has been blocked out, and these are the 4 planets. 1, 2, 3, 4 planets. At the bottom, you can see the year and date of observation. So 2009, and you will see that this date changes once I play the animation. Play it again. So that is 7 years of observation from 2009 to 2016. And you can see that the planets are revolving around the star. Okay, so focus on these 4 points. So what you are looking at are the first direct images of extrasolar planets ever taken, okay, by this team of astronomers. Without blocking the starlight, we will not be able to see these faint planets going around them. Now, another example of where we have actually seen the planet is Beta Pictoris, which is a star in our own galaxy, Milky Way. So here is Beta Pictoris, the star, and the light from the star has been subtracted or removed so that we can see the rest of the region. And this is the one of the planets around Beta Pictoris. What is drawn here is a scale, AU. AU means astronomical unit. Okay? And 1 astronomical unit is the distance between Earth and Sun. So this is roughly 3 AU. So if you keep this bar here, this is roughly about 9 AU or so. So that's how far away. So this planet is 9 times distant from the star compared to the distance between Earth and Sun. Here is the animation. You can see that the planet is moving relative to the star. So recently, direct imaging, direct pictures of extrasolar planets have also been possible. Okay. Now, the first extrasolar planet around a normal sun-like star was discovered in 1995. And since 1995, 25 years have gone by. And in these 25-year time period, great progress has been made in the field of extrasolar planet discovery. 25 years is not a long time span. Okay? In this, it's a very short time span. And in that short span of time, the number of extrasolar planets known to us has swelled by dozens to hundreds to couple of thousands. Today, we know about more than 4,200 extrasolar planets orbiting various stars in our own galaxy. So I want you to imagine that for a moment. Prior to 1995, the only planetary system that we knew was our own solar system. In a short span of 25 years, we have discovered more than 4,000 extrasolar planets, and that number is still increasing. So here is a histogram where the number of planets discovered is shown against year. And these different colors represent different techniques for detecting extrasolar planets. Radial velocity is red and transit is green. And so you can see that 1995 is when the first extrasolar planet was discovered. And after that, it has been an exponential growth in the number of detections of extrasolar planets, mostly dominated by transit method. 70% of the planet discoveries have come from transit method, 25% using radial velocity method, and the remaining 5% from a number of other techniques, including direct imaging. Now, the reason why transit method has been so successful is because of one particular space-based mission, which is the Kepler Space Telescope. The Kepler Space Telescope was launched in March 2009, and the Kepler Space Telescope is a space telescope. It's a telescope in space. It orbits the Earth and the Sun in what is known as the Earth trailing heliocentric orbit. So this orbit is about 160 million kilometers behind the Earth, trailing behind the Earth in Earth's orbit around the Sun. And from that vantage point, Kepler kept on observing about 150,000 stars, constantly monitoring their brightnesses. And based on those observations that lasted for nearly 10 years, 2018 October was the end of the mission. In that span of 10 years, Kepler discovered more than 2,500 extrasolar planets. So out of the 4,000 extrasolar planets we know, more than half the number of planets have been discovered by this one mission, which is Kepler Space Telescope. And all these 150,000 stars, they are all stars in our own galaxy, the Milky Way. Kepler was a really landmark mission. It really changed the field of extrasolar planet studies. And just to appreciate how important this mission was, let's look at two graphs. Okay, so this is the planetary mass is plotted on the y-axis here. So one means planets with mass comparable to the mass of Earth. This line represents planets with mass comparable to that of Neptune, and this is the line represents mass comparable to the mass of Jupiter. So any dot that you see here, these are all planets that have been discovered with masses greater than that of Jupiter. These are all planets which were discovered with masses greater than Neptune but less than Jupiter. And these are all planets that are discovered with masses greater than Earth, less than Neptune, and a few planets with masses similar to Earth. This is how the plot of extrasolar planets looked before Kepler Space Telescope was launched. After Kepler Space Telescope, the graph looks like this. Okay, all these yellow dots that you see, these are all the planets that Kepler Space Telescope discovered. What is most interesting is that in addition to the large number of planets that Kepler discovered, what is even more interesting is that many of those planets have masses and sizes comparable to that of Earth, which means that they are probably rocky terrestrial planets like Mars, Venus, and Earth. So for those reasons, Kepler was truly a landmark mission. And in terms of the future of this field, there are a number of missions that are already in the pipeline. Hubble Space Telescope, which is still there in space, launched in 1990. Hubble is still there, 600 kilometers above sea level, observing the universe from above Earth's atmosphere. Hubble is used for detecting extrasolar planets. Spitzer is also, which is another space telescope, is also used. Kepler was launched in 2009, got decommissioned in 2018. Currently, there is a mission that is flying in space called TESS, okay, which is a dedicated space telescope to discover extrasolar planets similar to Earth, okay, which means small extrasolar planets orbiting different stars in our own galaxy. In the near future, there are a number of other missions, dedicated missions, and also general missions for finding extrasolar planets. So the future definitely looks exciting in terms of the discovery potential in this field. So I'll conclude this presentation with one or two slides, okay? And I want to use this particular slide as a final takeaway message of this presentation. So even if you were to forget everything you heard in this presentation, okay, if there is one thing which I would like you to still remember, then that is the following. In the 25 years time that has gone by, what research in astrophysics or this particular field of extrasolar planet studies has taught us is that every single star that we see in the night sky probably has one or more planets going around it. It is just a matter of finding them. Detecting planets may not be easy, but it's not impossible. Okay? So this extrasolar planet discoveries that have happened in the 25 years, it's telling us that every star that we see in the night sky has planets going around it. All the innumerable number of stars, they are probably hosting one or more planets which are in orbit around them. The universe seems to be bursting with planets. And in fact, it won't be an exaggeration if I say that there are probably more planets than stars in our own galaxy, the Milky Way, because each star is likely to have one or more planets around it. And this particular fact is profoundly important because it enhances, if planets are so common in our universe, if they are more abundant than stars, then that really enhances the chances of finding an Earth-like planet around a distant star that can potentially be a safe haven for life. A planet similar to Earth, where water exists in its liquid form, with a dense atmosphere where perhaps, maybe, and that's a big maybe, that's a big question mark, maybe life as we know it is a possibility. So this is why this field is so important. And what is even more amazing is that the number of stars that we have so far searched for extrasolar planets is only less than 10% of the stars in the Milky Way galaxy. So imagine that this is our galaxy, Milky Way. If we could go out of our galaxy and take a picture of it, our Milky Way galaxy will look something like this, like a spiral galaxy. There are 200 billion stars in our galaxy. Okay? Sun is only one star in it. And we are located, Sun is located not in the center of our galaxy, but at roughly 30,000 light year distance from the center. For 2/3 distance from the center. This is where Sun is. And all the planets are. And all the 4,000 plus extrasolar planets that we have discovered in the last 25 years, they have been discovered by looking at stars in this vicinity of the Sun. So that's what I meant when I said that we have only looked at less than 10% of stars in the Milky Way galaxy. There are a lot more stars to search for. Okay. And so there is a looming question, okay, are we alone in this universe? Could there be intelligent life elsewhere in this universe? Asking these very same questions and discussing these kind of topics. At the moment, we don't know. We don't know whether intelligent life or life as we know it is present in any planets, but the detection of extrasolar planets is a crucial first step in understanding the possibility or the probability of it and keeping the search alive. So I want to end this presentation by quoting a very interesting, famous quote by scientist and science communicator Arthur C. Clarke. So when he was asked about the possibility of intelligent life elsewhere in the universe, he said that there are two possibilities. So either we are alone in this universe or we are not. Both are equally terrifying. Okay. So I'll end my presentation with that, and if you have any questions, you can ask.
Thank you, sir, for your wonderful presentation. And still, we are so curious to know whether there is any life in this space. And we are waiting for that. And we think that that answer will come from within few years. And next is our turn to the reporter, the new form of presentation today. And we have our Jairam sir, he is there, and he will act as a bridge in between the student and the panel and the presenter. And I invite Jairam sir for his for talk is for a few moments. Okay, thank you.
Thank you, Radial. Can you hear me?
Yes, sir.
Yeah. Thank you very much. As a rapporteur, that's a new introduction to this scheme of things. My duty is to capture the gist of the presentation today. And at the outset, let me congratulate Dr. Anand Narayan for the excellent and well-structured presentation and the way he has taken us on a voyage on the how to look at the exoplanets, how to cite them, and what are the limitations. Okay, just a highlight of his presentations were to start with, he has taken us on to what exoplanets are. And then also he gave us a good introduction of what astrophysics is and how it is about trying to find scientific answers to fundamental questions about the origin and the sustenance of the universe. Subsequently, he has taken us and told us about why observing exoplanets are important and what are the barriers, difficulties, and challenges in taking the direct images of these exoplanets. In view of the brightness and other issues involved. And also he has clearly told us about the methodologies of how to look at these exoplanets and how to get a picture of them and their characteristics in terms of the direct and indirect methods of observation. And basically he has highlighted the indirect methods of observation by the radial velocity method as well as the transit method, and how the spectrographic observations will help us to understand the blue shift and red shift and ultimately understand what the exoplanet activities are. Then also he has told us about the observation and the detection of the first of the exoplanet, the star 51 Pegasi and the exoplanets in the 1995, and how it led to the award of the Nobel Prizes for these people. And he has also highlighted what are the limitations of the radial velocity method as well as the transit method, and how 70% of the observations are attributable to the transit method and about 20% or to the velocity method, and then 10% only direct observations. Then also he briefly touched upon the Kepler telescope and how it's a mission and how it could help us to see about 2,600 exoplanets. And in the concluding session, he has told us about what the possibilities are that every single star we see has one or more exoplanets around that. And though it's not an easy task, but it's not an impossible task, and how the scientific community, with help from the advanced technologies in optics over the last 25 years, have are moving forward in detecting more and more exoplanets, and ultimately they are also in the pursuit of finding out whether any planet like our Earth, where life can be sustained, is around the corner. So this is the basic gist of what Dr. Anand Narayan has given us over the last 1 hour. I don't know how the time has passed. Anyway, it's over to our bright and intelligent children. Over to you.
Okay, thank you, Ram sir, for your reporting session. And I think the students get a gist of the presentation from your part. And next is the wonderful question answer session. That session is managed by our Sriram D. He's a student of our UL Space Club, and he's so happy today. I can see that yesterday he sent his mark list to me. There I could see that the maximum of the score and he secured is equal. That means he is full in his all the mark list, and I take this moment for congratulate him his academic excellence. And he's a wonderful speaker, and he is the first prize winner in the Kerala Universal for the previous year also. And I will proudly presenting our D. Sriram to handle this question answer session. Welcome, D. Sriram.
Thank you so much, Shajil sir. As you said, I am very happy today, and I wish all of you a happy, dear friends. I wish to say our sincere gratitude to our lead speaker, Anand Narayan sir. I heard your name firstly from a TEDx talk that based on the topic cosmic perspectives, and it was really undoubtedly a very nicely done presentation. And after that, I hear you are coming to take a session on exoplanets and habitable life situations in our webinar, 15th webinar. So I was also excited to see and hear your live session. Yes, of course, we all know the session was in depth and very well done. We thank to Anand Narayan sir. And we know that he is from IIST, Indian Institution for Science and Technology, Trivandrum, one of a most reputed institution in our state. So we all are, including me, interested in astrophysics. So some of interesting questions we got from the students, not so close to the core of the topic, but their inquisitiveness considering from our side. So I asking the first question from a student from the 10th grade MGM Higher Secondary School, Manitawadi, a 10th grade student, Han Joseph Anup. He's asked that is our solar system unique? Because in other systems, we found Jupiter-sized planets so close to their parent star, and we found super-Earths. What's your opinion, sir?
Yeah, so as I mentioned, the techniques that we use are biased towards finding big planets close to their star, hot Jupiters, and planets which are in short orbits. So that means that whatever information we are getting, we are only seeing one side of the whole story. There could be many planetary systems which are comparable, similar to ours, where we have small rocky planets at distances similar to Mercury, Venus, Earth, Mars, etc., and gaseous planets further out. But our current observational techniques limit us from detecting that. And we have only looked at about 200,000 or 150,000 stars for extrasolar planets. That's a very, very small number. So the current data is skewed, it's biased. Okay, that doesn't mean that big planets close to the star is the most common occurrence. There could be out there very well planetary systems comparable to ours. With improvements in technology, I think we may find them. So it's too early to say whether we are unique or not.
Okay, so one question from Han Joseph Anup again. He asked that, is it possible for waters to exist in a more distant region to the Goldilocks zone due to tidal forces? So the term habitable zone has to be extended, right?
Yeah, so for those of you who are not familiar, habitable zone is a term that is often used in the study of extrasolar planet. Habitable, we know that life on Earth is heavily dependent on water. So water is one of the primary ingredients for life on Earth. And so one question we can ask is there a distance from a star where water can exist in liquid form. If the planet is too close to the star, then all of the water will be in water vapor form because of the high temperature. If the planet is too far away, it exists in the form of ices in solid state. So what is that distance from a star where water can exist in liquid form? That is called habitable zone, which is also called Goldilocks zone. Okay. Now, there are some distant worlds within our solar system, primarily moons of big planets like Jupiter and Saturn. There is a moon of Jupiter called Europa, which is covered with water ice. And we know that on Earth, whenever we have water ice, beneath water ice, we have liquid ocean. So it's possible that beneath the icy surface of Europa, there could be liquid water where microbial life could be present. So those are the potential places within the solar system where in future spacecrafts may explore and dig for possible life forms. So the habitable zone, on the other hand, has a very fixed definition. Habitable zone is just the distance from a star where water can exist in liquid form, where based on some simple assumptions. It's just a convenient way of asking whether the extrasolar planets that we have discovered, whether they are too hot or too cold. There are a lot of uncertainties in it. For example, we know that the atmosphere plays an important role. If Earth did not have an atmosphere, Earth would be a very freezing planet. Without an atmosphere, the global temperature would be something like minus 18 degrees centigrade. Whereas the current global temperature is 15 degrees centigrade, making life possible. And that is because of the greenhouse gases present in Earth's atmosphere. So for the extrasolar planets that we are discovering, there is no way to right now measure whether they have any substantial atmosphere or not. So it's very difficult to say whether they are habitable or not.
Thanks, sir. We are moving to the next question we have. So it is actually from Navaneet S. Asking that, has anyone found planets revolving around a black hole till now?
Okay, so the two techniques which have been most successful, radial velocity and transit method, both requires observation of the star. We need light from the star to infer the presence of the planet. A black hole by definition is an object that doesn't give off any electromagnetic radiation, any light. So even if there are planets orbiting around black holes, we will not be able to detect them because we cannot see the black hole as a star, because it's a dead star and there is no light coming from it. So such kind of searches are not possible. But interestingly, if we leave aside black hole, there is another kind of dead star called neutron star, which is a very dense star that is made entirely of subatomic particles, primarily neutrons. And these are the end phases. These are the last, what remains when massive stars die, these neutron stars. And around neutron stars, planets have been discovered. In fact, the first extrasolar planet to be discovered beyond the solar system was around a neutron star. But that discovery was not that exciting because the star is already dead. Okay? So in 1995, astronomers discovered a planet around a sun-like star, which was more interesting, more exciting. It caught a lot of public attention because invariably it leads to the question of, is that a habitable planet, etc. So not around a black hole, but around other dead stars, people have found planets.
Okay, sir. We have another question from Navaneet, our student fellow of UL Space Club. Can you please explain more about the radio velocity method? Sir.
Okay, is there anything specific that Navaneet wants to know? I have basically explained. So the reason why it's called radial velocity method is because, as I showed in the animation, we record the light from the star, and that light shows shift in color towards blue and red, and that shift in color is converted into velocity. Okay, so that's how this term velocity comes, radial velocity. And that we're using that velocity and using some simple equations of Kepler's law, the mass of the companion planet, which we don't see, is inferred. So that's what this radial velocity method is, and it requires a telescope and a high resolution extremely sensitive spectrograph for those kind of measurements to carry out. So it's in a brief, that's all I can say.
Okay, sir. We have a question from Niranjana S, a 9th standard student at GHSS Naduvannu. So she asked that, will the technological development allow us to look at the surface of the furthest exoplanets in the 21st century? Like how we look at the surface of the Earth-like planets, so-called Kepler planets.
Okay, so that's a very interesting question. Okay, so in future, we don't know what exactly is going to happen, but what is currently happening as we speak is that astronomers are now able to measure the chemical composition of extrasolar planet atmospheres using transmission spectroscopy, a technique called transmission spectroscopy. So now we are no longer detecting the planet, we are also seeing whether the planet has an atmosphere, and if it has an atmosphere, what kind of molecules are present in the atmosphere. Now the reason why this is very interesting is because if you look at Earth, Venus and Mars, all three planets have atmospheres, but the main difference is that the atmosphere on Venus and Mars is dominated by CO2, whereas the atmosphere on Earth has large amounts of oxygen, molecular oxygen present. The reason for the buildup of oxygen on Earth's atmosphere is life. Photosynthesis is the main reason why Earth has so much of oxygen in its atmosphere. Photosynthesis by plants. Okay? So on Earth, the oxygen levels built up roughly 2 billion years ago when photosynthetic algae, which are very microscopic organisms, they started this anaerobic respiration where you give off oxygen into the atmosphere and you take in carbon dioxide. So that presence of life is what slowly raised the abundance of oxygen on Earth's atmosphere over millions of years. So now if we can detect extrasolar planetary atmospheres, and if we can find signatures of oxygen or water vapor in those atmospheres, then that is an indication that it possibly suggests that the planet has a biomass. It has life beneath it. So that is the cutting edge work that is happening right now. Extrasolar planet atmosphere detection is a very, very interesting field. And it is one more big step towards this question of how many of these extrasolar planets are potentially habitable or potentially are harboring life. Okay, so that's where we are. But in terms of seeing the surface of the extrasolar planet, it is very difficult because with the current telescopes, even stars look like point sources. Planets which are even smaller will look even smaller than a point. So we cannot see or resolve the surfaces of those extrasolar planets. We don't know. So whatever pictures I showed of extrasolar planets, they are all animations, computer images of those extrasolar planets, artist impressions. Okay, they are not real.
So we have a question from Abhijit EA from MGMHSS Manandawadi again. He's a 10th grade student. He asks that, sir, can't other objects in space block the lights while we use transit method?
Yeah, so that's very correct. Okay, so if some other object passes in front of the star, that can also block the light, which is why confirmation of an extrasolar planet using transit method requires repeated observations. Okay, so based on one-time dimming of a starlight, we cannot claim that we have found an extrasolar planet. Once a dimming is observed, they keep on monitoring the brightness of the star, and they'll see whether they can catch again this dimming happening. So repetitive dimming is what is claimed as an extrasolar planet detection, not one-time dimming. So chance passing of random objects in front of the star will be eliminated through this process. So there is a lot of checks and measures that are used before the detection is confirmed.
Okay,
Until the
sir.
detection is confirmed, it is only reported as a tentative detection.
Okay, sir. We have a question from another UL Space Club fellow, Adil. He asked that, is there any way we find a habitable pulsar planet?
Okay, so the chances of that is very, very small. Okay, so keep in mind that all our discussions are based on life as we know it here on Earth. Okay, so it's a very narrow definition of what life could be, but we can only be searching for what we know. Okay, we cannot really look for something that we do not know, and life as we know it on Earth is carbon-based life, water-based life, etc. So that kind of a life requires very stable conditions for survival. In the case of pulsar planets, that is neutron planets around neutron stars that I spoke about, the amount of radiation from these neutron stars is going to be so large that the planets that are orbiting around it are going to be constantly bombarded by high levels of radiation, making life extremely difficult. So if you talk about cellular life forms similar to that of Earth, these radiations will be very harmful, causing all kinds of mutations in our cells, making them completely dysfunctional. So unless there is a stable environment, a stable source of energy and a protective atmosphere around it, sustenance of life is very difficult. And so around pulsars, extrasolar planets which are discovered around pulsars, they are not the best candidates to, at this point, to look for life, because the star around which those planets are revolving are dead.
Okay, sir. We have a question from Adidev JD, a student from SVMEHSS Nenminda, a 10th standard student. He asked that, sir, can you please explain about Drake's equation?
Okay, so Frank Drake was an American astronomer, and he was one of the pioneers of a project called SETI, which is Search for Extraterrestrial Intelligence. This is a project where they tried to look at radio signals coming from intelligent civilizations which are somewhere else in the universe. And the reason for doing it is because we humans, we consider ourselves to be intelligent, and we are broadcasting into outer space. We are sending electromagnetic signals into outer space. Okay, the Olympics that happened after World War II, those television signals have now reached maybe 10 or 15 or 50 or 60 light years. Okay, so 1940 to now is roughly how many years? 60 years. So it has already reached stars that are 60 light years away. So consciously or unconsciously, we are broadcasting ourselves. So then people thought, okay, why don't we also listen to electromagnetic signals from intelligent beings who are trying to announce their existence by sending out electromagnetic waves. So thus this project SETI was launched, Search for Extraterrestrial Intelligence. Frank Drake was a pioneer. And so this project went on for many years, but there was no detection, no signal, nothing, no call from any extraterrestrial civilization. So people started really questioning the validity of this kind of an experiment. Okay, how long will we keep listening? So Frank Drake came up with an equation which is now called the Drake equation. It's not a mathematical equation, but it's more like a conceptual equation where he put all kinds of numbers, and finally that equation will give us the number of intelligent civilizations that are currently there in our galaxy. For example, he said, we know that life requires energy, so which means that life can only be present around a star. So how many stars are there in our galaxy? Take that number. What fraction of those stars have planets present? Before 1995, we would have said that maybe 1% of those stars have planets, but now we will say that maybe all 100% of those stars have planets. So then number of planets, how many planets will be Earth-like, how many will have atmosphere? So all these factors are put in. And finally, we ask this question, how many in those planets intelligent life will exist? Which is a big question mark. Nobody knows any answer to that. So that's what essentially the Drake equation is, and you can go and read about it online. It's a very interesting equation. So that equation is supposed to help us understand this question of why we are not detecting extraterrestrial signals from extraterrestrial intelligent beings. Okay, so that's what Drake equation is. I can go on and on about Drake equation, but I don't want to take a lot of time. So let's move on to the next question.
So there is one more question on the Drake equation by our winner of UL Space Club webinar quiz, Febin Firshad. He asked that, so why does the possibility of Drake equation changes? The quantity of each multiple today are in the same from that in 1950s. Drake speculated the sophisticated equation.
Yeah, so when Drake came up with that equation, he put a number of parameters. But as I said in my response to the previous question, the value that we put for those parameters have changed. For example, what fraction of stars have planets around it? Before 1995, if I was answering that question in 1990, I would have said that a conservative number like 1% of all the stars in our galaxy have planets. But now we know that planets are very common. In fact, they are more common than stars. So now if you ask me to put a number there, I'll say maybe 90% of the stars in our galaxy have planets around it. So with more and more information coming up, those numbers are getting revised. Okay? But the parameters have remained the same. The number of variables in that equation has remained the same. Only the value that we are putting in has changed.
Okay, sir. We have a question from Abhiram TP. He asks that, so how does the presence of methane indicate the presence of life?
Okay, so the source of methane in atmosphere is two. There are two sources. One is biological source and the other is non-biological source. Okay? So on Earth, the biological source of methane is, the process is called methanogenesis. The biological source of methane are certain bacteria which release methane gas into the Earth's atmosphere. The abiotic or the inorganic source of methane are rocks and some chemical reactions that happen on those rocks. So the presence of methane, these kind of gases, methane, oxygen, water vapor, there is a common name that astronomers use for that. They are called biomarkers, which means that if you detect those gases in a planet's atmosphere, there's a possibility that that particular gas or those particular molecules have come from life. So methane, a presence of methane on Mars or any other object within the solar system could indicate that there is microbial life present on the surface, which is why many Mars missions have focused, including our Mars orbiter mission, have focused on detecting methane on Mars's atmosphere. But as I said, it comes with a warning, which is that just because we detect methane doesn't mean that it is produced by life. There is a abiotic or inorganic process by which methane can be produced. But that's the reason why methane is so interesting. And also the other reason is that our early Earth atmosphere probably had some amount of methane in liquid form. And there is a hypothesis, it's not a theory, it's a hypothesis, an educated guess that the initial amino acids, etc., were synthesized in this primordial soup, which also contains methane. Okay, so for all those reasons, methane is very interesting molecule to look at.
Okay, sir. We have a question from Abhinav B. George, and a student from Alfonso Senior Secondary School. He asked that, can there be a star which has only one planet revolving around it, and will it have life in it?
Yeah, so surely anything is possible. You can have a star with no planets around it. You can have a star with one planet around it. You can have a star with 10 or 20 or 30 planets around it. Okay, it's all a question of statistics. So the odds of a star having a single planet is, I don't know what the number is, and that planet having life, that's a big question mark. Biologists have very pessimistic answers for that. Biologists usually say that life is so complex a phenomenon that the chances of it arising in another environment is very, very slim to none. So I don't know. I mean, unless we discover conclusive evidence for life, we cannot really say that what is the probability here. Okay, so I don't know more on that.
Okay, sir. We have another question from Febin Firsha that NASA says Nancy Grass telescope can be 500 times faster than Hubble telescope in search of exoplanets. How is this practicable?
Can you repeat the question again? I didn't get the first
Yes, sir.
part.
NASA says Nancy Grace telescope can be 500 times faster than Hubble telescope. How it is possible, or it is practicable?
So I don't know what is Nancy Grace telescope, something which I'm hearing for the first time, but I can comment on Kepler Space Telescope. Okay, so Kepler Space Telescope has been so successful because it is a dedicated telescope which was dedicated for the detection of extrasolar planets. So using transit method. Now the probability of discovering a planet through transit method involves a bit of luck. For example, suppose I'm looking at this part of the sky, one part of the sky, and I'm monitoring the brightness of a star for 1 or 2 days. I don't see the brightness changing. Now I move to another part of the sky and I'll be monitoring the brightness of stars there, but that is when the transit will be happening here. So the probability of detecting a planet through transit requires a little bit of luck. We should be looking at a star when the planet is transiting in front. So what Kepler did is, instead of randomly looking at stars, it looked at one patch of the sky where there are a lot of stars, about 150,000 stars, one patch of the sky, and it kept on looking at that one patch of the sky for the 10-year duration of its mission. It didn't look anywhere else. So that it will only find planets around those 150,000 stars, but then the chances will increase because you are constantly staring at that same set of stars. So you are likely to catch every single transit event that happens. Okay, so that way it is better than some of the ground-based telescopes. Okay, so but I don't know what a Nancy Grace telescope is. So sorry.
Thanks, sir. It will be an interesting subject to us also to research on that telescope. We also don't know that. Okay, and we are going to end the session by the last question from Bharat Srijit, our student fellow years. I welcome Bharat to ask his question.
Thank you so much, Sriram. I didn't expect you to invite me right now. So the question was very simple, nothing much complex. You had talked about the radial velocity method, sir, and you said I think it is more practical than the transit method in terms of accuracy. But sir, I have a doubt. What if the star planet orbit systems, the plane of the orbit is perpendicular to our line of sight? How do we calculate it if in such a case? Is it possible?
Yeah, so that's a very interesting question and a very involved question. So I didn't go into all those aspects because it will be too much. So in order to measure this wobble motion or the shift in spectra, the planetary orbit cannot be perpendicular to our line of sight. Okay? If the planet is orbiting in a plane that is in the plane of the sky, which means it's perpendicular to our line of sight, then we will not measure any Doppler shift, this blue shift and red shift. The planet orbit has to be at some inclination with respect to the plane of the sky. It will be really good if the inclination is 90 degrees with respect to the plane of the sky, which means the planet is coming in and out of the plane of the sky like this. But if not, it can be at some inclination. But if it's completely like this, where the planet is moving, the star is moving like that, perpendicular to our line of sight, then we will not be able to detect those extrasolar planetary systems. So that's another selection effect or bias in this radial velocity method. All the extrasolar planetary systems that we discover using radial velocity, they will all be either perpendicular, either along our line of sight or at some inclination less than 90 degree with respect to our line of sight. We will never discover extrasolar planetary systems that are in the plane of the sky, perpendicular to our line of sight using radial velocity method.
Okay, sir. Actually, we have a competition here in the chat box for the Q&A session. So finally, I will ask one more question from my sixth student Anika. She is asking again and again to ask her question. So,
Sure.
one of her question was, do we have any signs of water on Mars?
Sorry, I didn't hear that question.
Sriram, it's not getting.
Is there any?
You have some connectivity problem.
Okay, sir. I'll ask again. So the question was very simple. Do we have any signs of water on Mars?
So that's again a big question mark. So Mars, in many ways, is similar to Earth because Mars has seasons and Mars has ice caps at its poles. The north and south pole, there are ice caps. Okay, and there are also seasons on Mars. The tilt of Mars' orbital axis is similar to that of Earth. So there are a number of similarities between Mars and Earth. So this polar ice cap is not water ice, but it is dry ice, which means it's a solidified carbon dioxide, which usually exists as vapor in atmospheric pressure that we have here on Earth. But on Mars, since the atmospheric pressure is very, very low, water vapor is existing in the form of solid, okay, so as a dry ice. And so there is a dry ice present, and this ice is therefore not water ice. But what astronomers have found is that there are many channels and small rivulets on Mars which are similar to channels that are carved on Earth when water flows. So on Mars also we see a lot of these kind of channels and high resolution images taken by orbiters and landers on Mars, and also using telescopes here on Earth. So these small channels that look like channels that have been carved out of water shows that Mars was probably hotter and wetter in the past where liquid water flowed. At present, there is no evidence for liquid water flowing in large amounts on the surface of Mars, but there is a speculation that there could be subsurface. Beneath the surface of Mars, there could be water present in liquid form. So to my understanding, this is the current state of information about water on Mars, but I could be wrong because the last time I read about it was several months back, so there could be updates about it. But it's an interesting question nonetheless.
So that was the end of our Q&A session, sir.
Okay.
And really thankful for you for showing the patience to reply all our questions from participants, especially from the students who are in high school. I'm closing the Q&A session right here. We got many of questions. I am really sorry if I didn't ask your questions. Please post them in our Cosmos group, which is our WhatsApp group of UL Space Club itself. So we can have a good discussion on that. And if we have doubts, we will send to Anand Narayan sir itself. We think he will clear all our doubts. Okay, that's
Thank
it.
you, Sriram.
Thanks.
Okay, thank you, Sriram, for wonderfully handling this question and answer session. And generally, there is a doubt. Most of our participants are students, but some veteran participants also with us. There is a question whether there is a scope for answering, asking a question from the part of these veterans, and also there is a question maybe there. Can I ask in Malayalam? യഥാർത്ഥത്തിൽ നമ്മൾ മലയാളത്തിൽ ചോദ്യങ്ങൾക്ക് ഈ സാഹചര്യത്തിൽ ബുദ്ധിമുട്ടൊന്നുമില്ല. നാഷണൽ വെബിനാർ ആണ്. അപ്പൊ എനിക്ക് തോന്നുന്നു നമ്മുടെ ബഹുമാനായ ഉണ്ണികൃഷ്ണൻ സാറ് ഇവിടെ നമ്മുടെ പാർട്ടിസിപ്പന്റ് ആയിട്ടുണ്ട്. ഫിസിക്സ് അധ്യാപകനായിരുന്നു, റിട്ടയർ ചെയ്തിട്ടും സയൻസിനോടുള്ള താല്പര്യത്തോടു കൂടിയാണ് അദ്ദേഹം ഈ പരിപാടിയിൽ പങ്കെടുത്തുകൊണ്ടിരിക്കുന്നത്. അദ്ദേഹത്തിന് നേരിട്ട് ഒരു ചോദ്യം ചോദിക്കണമെന്ന് ആഗ്രഹമുണ്ടെന്ന് മനസ്സിലാക്കുന്നു. ഉണ്ണികൃഷ്ണൻ സാർ, പ്ലീസ് ആസ്ക് ദ ക്വസ്റ്റ്യൻ. ഹലോ ഉണ്ണികൃഷ്ണൻ സാർ. ഓക്കെ
സർ കേൾക്കാമോ? സർ കേൾക്കാമോ?
കേൾക്കാം.
ആ സർ,
ചോദിച്ചോളൂ.
വളരെ നല്ലൊരു പ്രസന്റേഷൻ ആയിരുന്നു സാറിൻ്റെത്. കേട്ടിരിക്കാൻ ഏവർക്കും തോന്നുന്ന ഒരു പ്രസന്റേഷൻ. അപ്പൊ അതിനിടയിൽ എനിക്ക് തോന്നിയ ഒരു സംശയം, ഇരട്ട നക്ഷത്രങ്ങൾ, അതായത് ആൽഫ സെന്റോറി, ബീറ്റ സെന്റോറി പോലെയുള്ള ഇരട്ട നക്ഷത്രങ്ങൾക്ക് ചുറ്റും ഏതെങ്കിലും പ്ലാനറ്റ്സ് ഉണ്ടെങ്കിൽ അത് ഈ പറഞ്ഞ രീതിയിൽ കണ്ടെത്താൻ കഴിയുമോ എന്നതാണ്. സർ.
താങ്ക് യു സർ. താങ്ക് യു ഉണ്ണികൃഷ്ണൻ സർ. വളരെ നല്ല ചോദ്യമാണ്. ഈ റേഡിയൽ വെലോസിറ്റി മെത്തേഡ് ഉപയോഗിച്ച് നമുക്ക് ഒന്നിൽ കൂടുതൽ ഗ്രഹങ്ങളെ കണ്ടുപിടിക്കുന്നതും പാടാണ്. ഒന്നിൽ കൂടുതൽ നക്ഷത്രങ്ങൾ ഗ്രാവിറ്റേഷണലി ബൗണ്ട് ആയിട്ടുള്ള ബൈനറി സിസ്റ്റംസിലൊക്കെ ഉണ്ടെങ്കിൽ ആ നക്ഷത്രങ്ങൾക്ക് ചുറ്റുമുള്ള ഗ്രഹങ്ങളെ കണ്ടുപിടിക്കുക എന്നുള്ളതും പാടാണ്. കാരണം എന്ന് പറഞ്ഞാൽ ആൽഫ സെന്റോറി, സാർ പറഞ്ഞ പോലെ ആൽഫ സെന്റോറി നമ്മുടെ സൂര്യന് ഏറ്റവും അടുത്ത് നിൽക്കുന്ന നക്ഷത്രമാണ് ആൽഫ സെന്റോറി, പ്രോക്സിമ സെന്റോറി എന്ന് പറയുന്നത്. ഇതൊരു ട്രിപ്പിൾ സ്റ്റാർ സിസ്റ്റമാണ്. മൂന്ന് സ്റ്റാർസ് അവരുടെ പരസ്പരമുള്ള ഗുരുത്വാകർഷണം കൊണ്ട് കറങ്ങിക്കൊണ്ടിരിക്കുകയാണ്. അപ്പൊ ആ കറക്കത്തിന്റെ ഇടയ്ക്ക് ഇതിന് ചുറ്റും ഒരു ഗ്രഹം ഉണ്ടെങ്കിൽ ആ ഗ്രഹത്തിന് കൊണ്ടുണ്ടാകുന്ന റിഫ്ലക്സ് മോഷൻ കണ്ടുപിടിക്കുക എന്ന് പറയുന്നത് വളരെ ബുദ്ധിമുട്ടാണ്, എക്സ്ട്രീംലി ഡിഫിക്കൽട്ട്. ട്രാൻസിറ്റ് മെത്തേഡ് വഴിയും ഡയറക്റ്റ് ഇമേജിംഗ് വഴിയും നമുക്ക് അത്തരം ഗ്രഹങ്ങൾ ഉണ്ടെങ്കിൽ കണ്ടുപിടിക്കാൻ പറ്റും. പക്ഷെ റേഡിയൽ വെലോസിറ്റി ടെക്നീക്ക് ഉപയോഗിച്ച് ഇറ്റ്സ് എക്സ്ട്രീംലി ഡിഫിക്കൽട്ട്. ഒരുപാട് ഡിസ്കസ് എനിക്ക് കേട്ടോന്ന് അറിയില്ല ആൻസർ.
കേട്ടു സർ.
ആൽഫ സെന്റോറി സിസ്റ്റത്തിന് ചുറ്റും ഗ്രഹങ്ങളെ കണ്ടെത്തിയിട്ടുണ്ട്. മൊത്തം 5 ഗ്രഹങ്ങളെ കണ്ടെത്തിയിട്ടുണ്ട്. 2 എണ്ണം ആൽഫ സെന്റോറി എ എന്ന് പറയുന്ന നക്ഷത്രത്തിന് ചുറ്റും, 3 എണ്ണം ആൽഫ സെന്റോറി ബി എന്നുള്ള നക്ഷത്രത്തിന് ചുറ്റുമാണ് കണ്ടെത്തിയിരിക്കുന്നത്. പക്ഷെ ഇറ്റ് ഈസ് എക്സ്ട്രീംലി ഡിഫിക്കൽട്ട്. ആ ഒരു റേഡിയൽ വെലോസിറ്റി ഉപയോഗിച്ച് കണ്ടുപിടിക്കുക എന്ന് പറയുന്നത് ബുദ്ധിമുട്ടാണ്. ട്രാൻസിറ്റ് മെത്തേഡോ അല്ലെങ്കിൽ ഡയറക്റ്റ് ഇമേജിങ്ങോ വഴിയേ ഇത് സാധാരണ എസ്റ്റാബ്ലിഷ് ചെയ്യാൻ പറ്റാറുള്ളൂ.
താങ്ക് യു സർ.
Thank you.
Thank you very much.
Okay. Thank you, sir. Then it's turn of our chief mentor, E.K. Kutty sir. I invite E.K. Kutty sir to make his reflection on this wonderful day. Welcome, sir. Kutty sir.
Thank you, Shadil Mash. As you said, it is a wonderful day. No doubt about it. An extremely knowledgeable, curious session which has enabled students to quench their thirst on what they wanted to know on very high pedestal science. In fact, this area, exoplanet area and exobiology area, are the two areas in which some of our students here used to bother me several times to get some right person to address them. I have failed in that. Today is the day where I have succeeded in getting the right person and who did a wonderful job today. So that way, today is a significant day for me for more than one reason. One is that Dr. Anand Narayan has come here and excited our students, and they have got stomach full of what they have been seeking. So that is why it is one important thing. Second important thing is the first stepping stone to IIST has opened up today. I have made a few attempts in the last 2 years, and certain things did happen, but not much. But today, Dr. Anand Narayan came on a request from a friend of mine, Deepak, a common friend. In fact, Deepak I had not asked Deepak anything on IIST or anything in the recent past, but on his own he understood that there is a need for a person of Dr. Anand Narayan, or a person of the type of Dr. Anand Narayan required amongst our students. He himself imagined it and made the proposal, and when I talked to Anand Narayan, he was more than willing to address our students. It is our luck, it is our pleasure, and it's such a nice thing. Now, soon after that happened, I got a call from Registrar IIST, Dr. YVN Murthy, that their Professor Kurian Joseph will be calling me. Very fortunate enough, his call followed and we spoke, and an arrangement is being made that we will having some talk from the IIST on 12th. Already we had arranged our MC Dattat a talk on 12th. I called him up and told that, sir, we will have some other occasion. He understands us. Yeah, he keeps coming to us for a very almost a lot of program. So he said that is fine. I said so that way IIST has opened up a new avenue for us. We used to get a lot of ISRO people, but almost all of them are gray-haired people. And our students are longing to get some young ones. So today that is also happened. And it is going to happen hereafter also. So IIST is sending people, their people are coming to us. Similarly, Dr. Somnath, the director of VSSC, has also given a list of 3 names. Young people, they are also going to address our students. That is the way I said today is a not only a very exciting session, a significant day for us. A lot of things are opening up for us. Now, I only wanted to tell a person like Anand Narayan that once the weather clears up and the epidemic disappears or it is under control, whatever it is, we would like to meet personally a person like him in IIST and kindly work towards that as the occasion comes, because our students are longing for such an opportunity. So it's a very exciting talk, very nice ambience Dr. Anand Narayan created here, and I'm extremely thankful for his readiness to come and address our students, and not only that, he named another very young student in his early 20s to come and address us. It was about to happen, but there are some small hitches in that. It may happen later. Otherwise, it was supposed to happen in the next 2 weeks, but we will wait for it. That again is a contribution from Dr. Anand Narayan. So that way, so this networking, the students, please note, your networking helps you to get the right kind of people whenever you need them, particularly when you are in knowledge and learning situations. So it's very, very important. So thank you very much, Dr. Anand Narayan, and thanks to the students who raised very good questions, and also the respectful teacher, Mr. Unnikrishnan also. Thank you very much. And this session is very well handled by our Bharat and Sri Abhiram. And I'm extremely happy. I'm extremely happy that our students are doing very well. And over to Shajil Mash.
Thank you, Kuti sir. These are the words from our chief mentor, and we are expressing our happiness. And next is a very important announcement is there. We can hear that the announcement from our student fellow, Bharat Srijit. Welcome, Bharat Srijit.
Thank you so much, Shajil sir. If you examine the chat box, you might have seen how many times I've typed important announcement to be made. Participants, please stay back. And in fact, it has worked because almost 60 participants were there, and most of them did stay back. So there are 2 announcements to be made. The first of which is about UL Space Quiz, the 15th edition of UL Space Quiz. Yes, sir.
Yeah. So can I exit now, or do I need to be here?
Sir, if you're busy, you may. I think some.
Does this quiz involve me, or is it separate from me?
We have a vote of thanks.
Yes, sir.
Okay, fine. Yeah, continue.
Another 2-3 minutes, Bharat, isn't it? 2-3 minutes.
Yes, sir.
Sure, go ahead.
If you can kindly bear with us.
No problem.
So the first thing is about a UL Space Quiz. We are going to have the 15th edition of the UL Space Quiz, which will the link is going to be sent right now in the chat box. If you examine, you might have seen that I have just posted the quiz link. Now, if you click on it, you will not be able to attend it. You will only be able to attend the quiz right after the vote of thanks. Go on. Just we have a few questions over there. Most of them which are directly related to the topic, and some of them we've stolen from Sir's presentation today. So you can go over there and type the questions, bag yourself prizes, and the first prize winner will get a cash prize, which is sponsored by Cinderbe Nurture. Now, the second thing that I would like to tell you is about a group that we, the student members of UL Space Club, has been maintaining. It is named Cosmos. It is based in WhatsApp, and we've had a lot of participants coming into the WhatsApp group from the webinars and other competitions that we have been conducting, and many of the participants from students who have watched today's presentation are already members of Cosmos, and they will tell you how effective the discussions and the topics that have been discussed in the group are. So if you are a space enthusiast, if you are interested in astronomy, if you're even interested in space travel and science as a whole, you can become a part of the group named Cosmos. So if you want to become a part of us, you could give me a WhatsApp message, and my WhatsApp number is given to in the chat box right now. So if anybody wants, or if anyone of your acquaintance wants to join our group, you may give a message to me on this WhatsApp number, and please take care not to share my number too much, because I'm going to get a lot of messages. So that is it from the two important announcements to be made. Over to Shadil, sir.
Okay, thank you, Bharat, for your important informations. And there is again, I think by next week we'll have a website for us for contacting us, and we are going to maintain. Next is we are just concluding this wonderful day, and then next is our vote of thanks. And this UL Space Club is an outreach activity of the Vagbadan the Edu project that is under the nurturing of Uralingal Labor Contract Society that already mentioned at the beginning of this webinar. And the Uralingal Labor Contract is so interested in nurturing especially the rural, eminent and rural bright students or gifted students from the General Education Department. And T. Damodaran sir is the coordinator of Vagbananda Edu project here. He is with us, and I invite Sri T. Damodaran sir to make his vote of thanks to our chief guest and all the participants. Welcome, sir.
Thank you, sir. Good afternoon, everybody. First of all, I express my gratitude to every person who participated in this webinar. The excellent presentation of Dr. Anand Narayan made this webinar a remarkable one. It was very informative and interesting to students. The question and answer session also was very effective. On behalf of ULCCS Foundation, with pleasure, I extend our sincere thanks to Dr. Anand Narayan. Thank you, sir. Thank you very much. Jairam sir done his part as a reporter very well. He gave a very brief report of what the chief speaker put before us. I am happy to thank him on behalf of ULCCS Foundation. Even though he is always with us, I thank him with pleasure for his good job. Master Abhiram presented the question with good energy and made the session very live. I also thank Abhiram for his good deed. I thank all the participants of this webinar, students and veterans and others. Moreover, I thank all the persons worked behind the success of this webinar, like Kutisar, Shajil Master, Bharat, Abhiram, Adil Krishna, and others. I thank Cinderbe Nurture for providing gifts to quiz winners. Once again, I thank all. Thank you all.
Yes. Then all of you will be maybe curious to know what will be the next week topic. I invite again Kutisar to declare the next week topic for you. Kutisar, please.
Hello.
Yes, sir.
Hello.
Yes, sir. Hello. Yes, sir. Okay.
I actually, I'm very sorry, I missed it. I ought to have said it about it. Now, the next talk is by Mr. G. Prasanna, a senior scientist, working scientist of VSSC. He is going to talk on maths in nature, life, and of course in space. I'll repeat, maths in nature, life, and of course in space. That is the topic. So please come as usual at 3. You can listen like Anand Narayan, a young scientist who is working in the area. Very interesting talk. Thank you. Thank you.
Thank you, good
That's
sir. Now we
That's all.
are
That's all.
concluding these things, and we are so happy to be here with you.
Thank you very much, Dr. Anand. You can.